Hi, today we are going to start looking at indefinite integrals. So if we have capital F prime x equals f of x, then for derivative of capital F of x is f of x. And we can say for indefinite integral of f of x is capital F of x. Now, our indefinite integral is sometimes referred to as the antiderivative. Now, if capital F of x is an antiderivative of f of x, then f of capital F of x plus c is also an antiderivative of f of x, where c is a constant. So we can say if capital F prime of x equals f of x, then our integral, which this is our symbol for an integral, of f of x d of x is equal to f of x plus c, where once again, this is our integral sign, f of x in here is referred to as our integrand. X is our variable of integration, and c is the constant of integration. So if our derivative with respect to x of x cubed plus c is 3x squared, we can say the integral of 3x squared dx is equal to x cubed plus c. So if we have it set up like this, we can say that our integral takes it this way, while our derivative goes this way. So we can see why our integral is referred to as an antiderivative, because it's doing the opposite operation that our derivative does. Now, some basic integration formulas. If we have integral of a constant times d of x, that's just going to equal a constant times x plus c. If we have integral of x to the power of n dx, then that ends up being 1 over n plus 1 times x to n plus 1 plus c. Now we can see with both these examples, if we take the derivative of what's on the right side, we get what's on the left side. Same as our integral of 1 over x with respect to x is equal to the natural logarithm of x plus c. Okay, properties of indefinite integrals. If we have a constant integral of a constant times a function, in fact, dependent on x, d of x, then that's the same as if we factor out that constant and take the integral of f of x. Same as if we have integral of two functions adding or subtracting together, we can break that up and say it's an integral of one function plus or minus the integral of other function, depending on whether we're adding or subtracting an integral function here. Now, for example, we want to evaluate. We have integral of 4x cubed minus 6x squared plus 11 d of x. So we want to work backwards. So we know that with derivatives, we reduce our exponent by 1. So with integrals, we're going to increase it by 1. So this would be x to the power of 4. And then normally taking the derivative, we'd have this come down in front. So that's where we got that 4 there. So I've got 4x to 4. And then we know that this would be x cubed. So if we brought this forward, we have to think of what times 3 is going to give us that 6. So that'd be a 2. And then we know this would be 11x. And then we've got plus a constant. This one, similar idea. We know this will be x cubed. And we want to figure out what, when we bring it the 3 in front, will multiply to give us 2. So that'd be 2 thirds. And then this would be x squared. But we don't have a number in front, so therefore we must have 1/2 in front of here. So when we bring the 2 in front, it cancels out with that 1/2. And then if we have a constant, we just know that that's going to be 7x. And then we'd have plus a constant term at the end. Okay, so we've got 2 more integrals on this page. So we've got the integral of cos x minus sin x d of x. So we know if we're taking a derivative of something and end up with cos of x, that's sine of x. And we know if we take the derivative of something and get sine of x, that's cos x. Now, when we know that we take the derivative of cos, it gives us negative sine, so we know that that's just plus sine x. And then we'd have plus a constant. Now, for this next one, I realize I have a mistake. It's supposed to be negative 3e to the negative x plus 6e to the power of 2x d of x. So we have to start, we can factor out the negative 3. And then we'll look at this. We know our derivative of e to negative x is e to negative x, so we know that that doesn't change. We know we would have our chain rule, so we'd have a negative come in front here. So therefore, I know that I would need a negative 1 here to cancel off that negative. And then over here, we know that we'd have e to 2x. And we know what from chain rule we got 2 from here, so therefore we must have a 3 here that multiplies by that 2 to get this. So simplifying this a bit, that gives us 3e to negative x plus 3e to the 2x. And then we have, I forgot to add the constant on both of these. Okay, next example, we've got the integral of 2 over x squared minus 5 over x plus x dx. Now, if I have a situation like this, I tend to like to rewrite it with negative exponents. So I've got the integral of 2x to negative 2 minus 5x to negative 1 plus x. And that's our derivative with respect to x. So we know that our x down here would be 1 greater, so this would be x to negative 1. So we know when this moves in front, it's bringing negative with it. So that means we would need a negative 2 here. So when it multiplies, that gives us a positive 2. Now, if we have a derivative that's giving us x to negative 1, that's our natural logarithm. So we know this would be negative 5 times the natural logarithm of x. And then this one, if we have x here, that means that we should have an x squared. And in order to cancel the 2 that's coming down, we need a 1/2 in front, and we'd have plus c. So we'll now rewrite this. So it'd be negative 2 over x minus 5 times the natural logarithm of x plus x squared over 2 plus c. Now to make things a little easier, we'll look at some equations that are on your integrals tables. So integration of exponential functions, if we have integral of e to x dx, that's just equal to e to x plus c. Of course, if we have a value up here with our exponent, we'll have to do chain rule. If we have a term to the power of x, dx, and that's in our integral. That becomes a to x over the natural logarithm of a plus c. And integration of trigonometric functions. If we have integral of cos x d of x, that's just sine x plus c. If we have integral of sine x dx, that's negative cos x plus c. Integral of secant squared x dx is equal to tan x plus c. Our integral of cosecant squared x is equal to negative cotangent x plus c. We also have our integral of secant x times tan x d of x is equal to secant x plus c. We have our integral of cosecant x cotangent x dx equals negative cosecant x plus c. Our integral of tan x dx is equal to a natural logarithm of secant x plus c, which can also be written as natural logarithm of cos x plus c. And then we also have integral of cotangent x dx is equal to natural logarithm of sine x plus c, which is the same as negative natural logarithm of cosecant x plus c. And we have integral of secant x dx equals natural logarithm of secant x plus tan x plus c, as well as our integral of cosecant x dx is equal to natural logarithm of cosecant x minus cotangent x plus c. Now, we can also keep in mind Pythagorean identities because we know from Pythagorean identities, for example, tan squared x is equal to secant squared x minus 1. So therefore, if we have integral of tan squared x dx, that can equal our integral of secant squared x minus 1 dx, which would just be tan x minus x plus c. Same as from Pythagorean identities, if we have cotangent squared x is equal to cosecant squared x minus 1, that therefore means that the integral of cotangent squared x equals the integral of cosecant squared x minus 1 equals negative cotangent x minus x plus c.